So welcome back. I hope you enjoyed the break and had made the most of your time to visit the booths or have your one-to-one meetings. The break was kindly sponsored by WR Grace. So this session is part two of achieving sustainability in a challenging market environment. We have three presentations once again in this session. So allow me to introduce our speakers. First up, we have Colin Bailey, Portfolio Manager, Environmental Additives from Grace, and his presentation is titled Super DSOX CV Plus for FCC SOx emission control. Next up, we have a presentation from Clariant from Mr. Paolo Corvo, who's Head of Sales and Marketing, and his presentation will focus on cellulosic ethanol made from agricultural residues, Clariant's sunliquid story. And to close out the session, it's my pleasure to welcome Eva Anderson from Alfa Laval. Eva is Refinery Industry Manager, Global Technology, and her presentation today will focus on maximizing the efficiency in all phases of biofuel production. So a warm welcome to all our speakers. Enjoy the session, and please do not forget there is a Q&A at the end of the three presentations, so send those questions in. Thank you.
Thank you for the introduction. Hello everyone. Thank you for taking the time to view this presentation about reducing SOx emissions in the FCC unit. The presentation is in two parts. The first part will focus on new product development in SOx additives, while the second part will describe some of the recent commercial case studies from these new technologies. So SOx reduction additives are particles very much like the FCC catalyst with similar physical properties. However, they contain considerably different chemical functionality, and this functionality allows the SOx additive particles to capture SOx molecules in the FCC regenerator, transfer them over to the reactor side of the FCC unit, and the SOx species are converted through a series of chemical reactions into hydrogen sulfide, and hydrogen sulfide is released with the FCC product. SOx reduction additives are very convenient and an effective method for SOx emission control, and they allow refineries to achieve compliance without the need for costly CapEx investment. SOx additives can be quickly introduced to the FCC unit, either pre-blended with the base FCC catalyst or through a separate addition device. And the unit response to the SOx additives is very quick. So you can see a drop in SOx emissions very quickly. The SOx additives are highly flexible in this sense. So at short notice, for example, if a refinery would be processing higher sulfur feeds, SOx additives can be quickly used to achieve the necessary compliance. So SOx additives are generally referred to in the industry as DSOX additives, but actually the term DSOX is a Grace trademark. This is technology that Grace developed. It was the first SOx reduction additive to be commercialized and patented. But in the meantime, Grace has made various advances in FCC SOx additives. But one thing that has remained constant is the magnesium alumina spinel backbone that the technology is built on. And I will discuss that in more detail in a few slides. So Grace SOx additives are very well established in the industry. They are the benchmark in terms of SOx reduction performance. They have been applied in a wide variety of FCC units, for example, those that operate in full burn, partial burn, as well as two-stage regeneration, and they can be applied for a wide variety of feedstocks, so for heavy feeds, light feeds, anything in between. But one thing to mention is that FCC is a core business for Grace as a company. So we not only continue to invest in our FCC catalyst technology, we continue to invest in our additive technology as well to remain the leader in terms of FCC technology. And I think this is highlighted nicely in the next slide. So 2 years ago, we made a significant capital investment in our SOx additive manufacturing facilities, where we introduced an additional processing step. This resulted in a SOx additive with enhanced properties and which resulted in step-out performance in commercial units. We launched this product under the name of Super DSOX CB+. The CB signifies increased dispersion of cerium and vanadium functionality across the additive particle, as highlighted in the slide. So here we can see the chart at the top. This shows pilot plant testing, and it shows an additive with high and low dispersion of cerium and vanadium. So you can see the lower dispersion is the blue line, the higher dispersion is the green line. So when you perform pilot plant testing, you start off with a baseline level of SOx, and this is followed by a one-time injection of SOx additive. Then you can see an initial drop in SOx emissions. This is a function of the SOx reduction activity. And then this is followed by a period of slow decay in activity. And this highlights the effectiveness of the additive for regeneration. So it can be seen for both vanadium and cerium, an increased dispersion allows the additive to retain its activity better, which results in lower SOx emissions. So the improved dispersion of cerium allows a better oxidation of the SO2 to SO3, while an improved vanadium helps with the additive regeneration. And both of these are very important in the SOx reduction mechanism. The more homogeneous distribution of cerium and vanadium can be seen at the bottom here in the EPMA elemental mapping images. We have Super DSOX on the left side, Super DSOX CB+ on the right side, and then for each you can see the elemental mapping of cerium and vanadium. So for Super DSOX CB+ on the right, you can see less cold spots in blue and less hot spots in red compared to the previous product on the left, and this highlights the better dispersion of these elements. An additional benefit of the process modification is the optimized spinel content. So I mentioned at the beginning that gray SOx additives are based on a magnesium alumina spinel backbone. So this is the crystal structure that the magnesium, aluminium and oxygen atoms form, and that's shown on the left here. And this is different from alternative SOx additive technologies. The graph on the right is taken from one of the fundamental academic research papers that was published in Industrial and Engineering Chemistry Journal. It plots SOx reduction activity as a function of temperature and shows that spinel-based technology, which is shown in green, can achieve the same SOx reduction activity at a lower temperature. And this highlights the superior additive regeneration obtained with spinel-based SOx additives. Slide 5 shows the XRD pattern for Super DSOX in red versus the improved CB+ in blue. The magnesium alumina spinel peak is at about 45 degrees, with free magnesium oxide appearing as a shoulder on the left, and there is a second peak associated with magnesium oxide at around 60 degrees. So grey SOx additives contain magnesium both in the form of magnesium alumina spinel, as well as in the form of free magnesium oxide. So the XRD pattern here for CB plus clearly shows a lower intensity for magnesium oxide peaks, which means that more of the magnesium is tied up in the spinel form, which is beneficial for performance. This is a table of refiners that have switched from non-Grace SOx additives to Super DSOX CB Plus over the last 2 years. There have been 13 back-to-back trials to date, and in each case the Grace SOx additive has been successful. The step-out performance that we are achieving with the new technology is remarkable in some of the trials, and we are gaining a lot of momentum in this technology segment. In addition to these trials shown in the table, we also have a couple of additional Super DSOX CB Plus trials lined up in 2020, which are expected to start in the fourth quarter. And as well, the additional processing step that we introduced to the manufacturing facilities has allowed us to pursue some additional new technology leads. And through ongoing R&D projects, we are hopeful that we can launch the next technology advancement in 2021. So moving into the second half of the presentation, I will give a brief discussion of some of the recent case studies that I have been referring to. So one of the initial trials that took place was at Refinery A in North America, and this began in March 2019. This is a case study that the refinery gave us permission to publish, which we did so in the fourth quarter edition of Petroleum Technology Quarterly. It's an FCC unit that operates in full burn, and the refinery initially switched from the non-Grace SOx additive to the CB Plus at a 1-to-1 replacement rate. The graph on the top left shows SOx emissions over time, switching from non-Grace additive in the blue dots to the Grace additive data points in green in March 2019. So it has to be said that the incumbent additive did allow low SOx emissions to be obtained, with average values slightly below 10 ppm. Switching to the Grace additive, the low SOx emissions were maintained, actually with an even lower average value of below 5 ppm. But also noticeable is the consistency of the low SOx levels. This is even more impressive when looking at the graph next to it, which shows the daily SOx additive addition rate. So these lower SOx emission levels were actually achieved at historically low levels of SOx additive usage rate. SOx additive efficiency is typically measured by pickup factor, or the PUF, and this is a value that represents the mass of SOx molecule captured per mass of SOx additive used. And you can see in this example, a significant increase in pickup factor was seen. The three lower charts show ECAT data. So ECAT is the circulating equilibrium catalyst in the FCC inventory, and this is analyzed on an ongoing basis. So we can see in the ECAT data a drop for the magnesium, vanadium, and cerium values. And these are elements from the SOx additive that can be tracked in the ECAT. And for each of these elements, a drop in the content can be seen with the switch to the Grace additive. And this reflects the lower additive usage rate and hence the lower additive concentration in the circulating inventory. The four charts in this slide plot the SOx emissions versus various key parameters. So first of all, the importance of SOx additive rate is fairly obvious. Moving along, the feed sulfur represents the source of the sulfur in the SOx. and then the slurry sulfur levels typically correlate very well with the baseline uncontrolled SOx emissions. Finally, the oxygen level in the regen is an important parameter, as it can be a rate limiting factor for SOx reduction, particularly at lower levels of oxygen of 1 and lower percent. But really the conclusion here is that whichever way you look at it, at comparable conditions, the Super DSOX CV Plus is delivering lower SOx emissions than the previous additive technology. The refinery subsequently decided to use CV Plus on an ongoing basis, and they continue to see excellent results. To briefly summarize some of the more recent trials, I'm showing two here that are applications in full burn. One was a trial in North America that started in 2019, and the other is a trial in Europe from this year. But in both cases, the SOx additive efficiency, or the pickup factor, increased by more than 50% with the switch to the Grace CV+. And finally, two applications are shown here in partial burn. So I already mentioned that partial burn applications can place more demands on the SOx additive due to the lower oxygen levels in the regen being a rate limiting factor in the SOx reduction mechanism. Both of these trials are from 2020. The first one is from North America, where the CV Plus delivered lower SOx emissions, and this allowed the refinery to reduce caustic consumption in the wet gas scrubber. So this is actually a refinery that uses a combination of SOx additive and caustic wet gas scrubbing for overall SOx emission compliance. Refinery 4 is from Europe, and this is the most recent trial that we have. It is at a fairly early stage of the performance evaluation, but we are seeing initial encouraging signs for the CV Plus performance. So to conclude the presentation, Grace has made significant advances in SOx reduction additives, and we continue to look into new R&D projects, so we are the forefront additive supplier for SOx additive technology. Our latest Super DSOX CV Plus is achieving step-out performance in various back-to-back trials versus non-Grace products in both full burn and partial burn applications. So thank you for listening. I look forward to answering any questions in the Q&A session or at any other points during this virtual conference. Thank you.
Thanks for the presentation. Good afternoon, everybody. Today I will be guiding you through some slides and showing you our lignocellulosic ethanol technology, which is called sunliquid, which is, in a nutshell, conversion of lignocellulosic biomass or waste streams into sugars to ethanol. Before I do that, let me give you a snapshot on on the company that I'm representing, which is Clariant. Clariant is a Swiss-based specialty chemical company. We are present in with three main business areas, which are care chemicals, natural resources, and catalysis. And that's where the business line biofuels and derivatives is located within the catalysis area. We are providing receiving sales for more than 4 billion francs. It's a big company, something in the range of 12,000 people, employees worldwide, 2019, and we are producing in roughly 66 production sites worldwide. Why have we been addressing and looking for solutions into advanced biofuels? Well, you're probably well aware of one of the important topics when it comes to needs to decarbonize transportation. Why is this the case? If you look into the overall percentage of greenhouse gas saving emissions worldwide, well, 24% is actually part of the transportation sector. And if we look into Europe, 27% is actually the number. So this is a big concern. There are different solutions that address this concern. You can see here on the right that solutions that are enabling to achieve and decarbonize climate are certainly ambitious targets to be achieved. We believe that in addition to vehicle technology and efficiency, energy infrastructure efficiency in development, and also different modes, and so shifting transportation modes, advanced biofuels, and more specifically lignocellulosic ethanol, is certainly the solution that plays the most important role in decarbonizing the transportation sector. When there's an issue in the environment, this is very well linked to legislation needs. So if we look into the world map, and if we focus on how our legislators supporting advanced biofuels, then this is what we currently see as we speak. China, there's a clear national requirement to go into an E10 mandate. So that's been spread out of the different provinces. India has set a national biofuel policy back in 2018 with specific requirements to build up 12 second-generation ethanol plants by 2022, and public tenders are ongoing as we speak. Then we have the Americas, North America, and more specifically, certainly with California as one of the key areas or as a benchmark when it comes to acceptability and interest into advanced biofuels. South America with renewed renewable RenovaBio legislation that came into force in 2020, which is requiring to double the volumes of ethanol in the country. And then finally, we have Europe, which is by far one of the benchmarks when it comes to renewable energy requirements and advanced biofuels. How does it look like when it comes to Europe? Well, there's a clear renewable energy directive which sets targets starting June next year. And these targets require mandated parties to blend in biofuels, either conventional biofuels, so the so-called food-derived linked biofuels, setting a target mandate by 2030 of maximum 7%. The target requires also a max, so a capped mandate of the so-called biofuels that using NX9B feedstock. I'll come back to that later. And then finally, we have a minimum target, so not a capped target, by 2030 of 3.5% of the so-called NX9A. What are these NX feedstock? It's a clear list of agricultural residues and waste streams that can be utilized with non-mature technologies to convert these feedstocks into advanced biofuels. And here you can see just some straw bagasse, nutshells, corn cobs, or other non-food cellulosic materials. All of these feedstocks can be converted with sunliquid technology, with a technology that I will be presenting in the next slides. While the part B are using mature technologies and mainly use feedstock such as used cooking oil and animal fat categories. If we were to use the available agricultural residues and waste streams in Europe and use the 3.5% with advanced lignocellulosic ethanol, then this would be a market of roughly 10 million tons of cellulosic ethanol in 2030. So very important market. So we understand the issue. There's policy. What would a solution be? Well, this is our solution. It's the sunliquid solution. In a nutshell, we pre-treat without any chemicals agricultural residues or waste streams products. We have a completely integrated enzyme and microorganism production, so it's process integrated. We then basically disrupt these fibers into sugars, and then fermented into ethanol to produce ethanol at quality specs for transportation use. There are side products to the process, and you can see here mainly it's lignin that used for burning. This provides all the energy needs to the system. There is CO2 that can be utilized, either captured or utilized. If we do capture the CO2, the overall greenhouse gas saving of this process provides a lignocellulosic ethanol that is 120% greenhouse gas saving. And then we have vinasse, which is fermentation sludge. It can be brought back in the field as a biofertilizer or used as energy or as a biogas source. Sunliquid is a conversion of this feedstock into ethanol for transportation, but it's also what we call a platform. So we do also commercialize the sugars for those to be converted into other bioproducts or ethanol that is not going into engines, but it can also be converted into other bioproducts. So in the middle, you can see here which are the downstream products and bioproducts that can be produced. Some of the example projects and collaborations we're doing with third-party customers and application fields. So this is really enabling to open up the Sunliquid platform to additional further opportunities. Where are we testing these feedstock, or what have we been doing in the last year? So we started back in 2006. 2009, we constructed our pilot facility. In 2012, we started up our pre-commercial site. The picture on the background is taken from our Straubing facility in Germany. So we've been testing different type of feedstocks, and here you can appreciate some of these feedstocks that have been tested into this 1,000 tons of ethanol per annum output production site. So we validated the process, we validated the results on the conversion of the feedstocks to sugar to ethanol. And this really has been serving as a testing site and also as a training site for our customers. So the customers bring their own feedstock here. We tested it. We provide back the results and also the samples. And this is the base for us to then start our license and service contract based on the results obtained in the facility. The natural next step was to go from this pre-commercial site to a commercial site. So this is what Clariant has decided to do, to invest its own money in a plant that we are constructing in Romania. This will be a 50,000 tons ethanol facility using locally sourced feedstock. This will create a substantial number of jobs, will be our first of its kind plant, and will be used as a training facility also for our customers. The pathway to where we're at now, the decision and approval was back in 2017. We broke ground in 2018. We started harvesting the amount of feedstock necessary on the field. This is an area, Podari, Romania, where the straw is left on the field, so we had to construct the whole value chain. This is a good learning activity for us to be deployed and brought to the market to others, to our customers. As we speak, we are into construction, and we are then expecting to complete the construction by 2021 and there onwards start the production. I told you that we had to create and complete the value chain, and that's what we're doing with a dedicated team. And this asset that is internal to Clariant is brought back on the market so we can supply our prospects with knowledge and support them into the creation of the value chain. Now I would want to show you a latest drone video that was taken some days ago in Romania so that you can appreciate the construction progress at the site. Good. So we're quite proud to be able to show these pictures, this drone video, sorry, because despite the terrible times of Corona throughout these months, we were able to continue the construction of the site, of course, with all the requirement measures of safety, both to our employees, but also to the construction site workers. So our responsibility is not only to build, construct this site and showcase this facility as a training facility for our customers, but it's also to bring the technology to the market by licensing, so by selling licenses. And this is what we've done. We already sold these 3 licenses in Europe to different players. So the first one that was sold to Envira, this is a first-generation ethanol and biodiesel player. So it's a 50,000 tons ethanol facility in Slovakia. The second one in Poland to a mineral oil player. It's a 25,000 tons per annum straw sourced, locally sourced feedstock site. And the last one that was sold in Europe is to Etabio, which is a Bulgarian company, which is one of the major players in the Bulgarian agricultural sector. So I think this is important to state that you see that sunliquid technology has been sold to different players throughout the whole value chain, from feedstock to first-generation ethanol players to mineral players. And the other license, or the fourth one that was sold, has been sold in China to a joint venture formed by the Guozheng Group and Chemtex Chemical Engineering. This is it's a 50,000 tons ethanol facility with an option to double the capacity in a second phase, based on wheat straw and corn stover. Getting to conclusion, what we bring into the market, while we support customers, prospects that are interested into developing these projects worldwide, with support to all the value chain. So from the assessment on the development of the feedstock to the contractual negotiation, all the way to the production and operation of these facilities. So I'm happy to be able to support you with questions should you have, both here during the conference, or here you have my contact details, and I'll be able to answer any questions. Thanks to all of you.
Hi everybody, and welcome to this Alfa Laval presentation, how to maximize profitability in your HVO production. It's going to be a rather quick overview, and of course we will have a Q&A session afterwards, but if you have more questions, please do not hesitate to either come to our e-booth here in the conference, or contact us directly on by sending a meeting request or an email if you have more questions. We will be more than happy to discuss how we can help you with your HVO production. So in this presentation, we will cover mainly 3 topics. We will talk about the pre-treatment, how you can maximize the feedstock flexibility for your plant. We will talk about how you can maximize the efficiency in the fractionation section of your HVO unit. And we will talk about how you can maximize the recycle and the reuse of water in your plant. All of this is aiming to give you the maximal feedstock flexibility, the longest catalyst life cycle and selectivity, maximize the product yield, maximize energy efficiency of the plant, minimize capex of your investment, and minimize the waste and environmental footprint of your HVO unit. So if we're starting with a quick overview of the HVO complex, you have, of course, in the center here, you have your HVO processes, which is a combination of a hydrotreater and an isomerization unit. That needs to be fed, of course, with hydrogen, You might have hydrogen available already in your plant, or you need to have an on-purpose new hydrogen production unit for your HVO complex. Same goes, of course, with the sulfur recovery. You are going to need to have a sulfur recovery section, either with spare capacity in an existing plant, or you need to build a new on-purpose sulfur recovery unit for your HVO plant. But what we will focus on in this presentation today is the feed pretreatment section, which is, of course, very different and very new for you refineries. How to give you the best flexibility for different kind of feedstocks that are being used in your HVO processes. And then, of course, the wastewater management. That's also going to be a little bit different to what you are used to with normal refinery wastewater. If we start with the feed pretreatment, the feedstock flexibility, that is going to be the key parameter to make your plant as profitable as possible. Selecting the right feedstock, depending on what product you want to produce, depending on what kind of availability there is in the market, and depending on what kind of plant you are going to run it in, is going to be key. There are different kinds of feedstocks. And of course, seed oil is one of the most commonly used feedstock. And among the seed oils, crude palm oil is by far the most popular feedstock for HVO production. One reason is because it has a very low phosphate content. So it has little impurities and require only very little pretreatment needs. It has also a high availability in the market, and it has a high energy intensity. So you will get a high yield of products if you are feeding your HVO unit with crude palm oil. But of course, for obvious reasons, there are other concerns with crude palm oil as a feedstock. There are environmental concerns, and there are also policies that might even block you from using crude palm oil as a feedstock to your plant. It means you might start to look at other kind of seed oils, such as rapeseed, corn, sunflower seed, which are all available in the market, but they are having a higher phosphate content. And with a higher phosphate content, it means you're going to need more pretreatment steps in order to remove impurities that could otherwise poison your catalyst or create fouling in your process equipment. There is also, with other seed oils, the food versus fuel debate. So it might also becoming less and less available, the seed oils that are also competing as feedstock or for food, and they won't be available to be used for fuel production. Therefore, more and more people are starting to look into waste products to feed their HVO unit. One such waste, which is very interesting, is distilled cotton oil. It's a waste from ethanol production. And this feedstock has a very high content of free fatty acids, up to 15%. That's both good and bad, because with a high content of free fatty acid, you will actually minimize your propane production in your HVO unit. So it actually means less byproducts, and you can reduce the reactor size. On the other hand, if you are planning to operate the HVO in an existing hydrotreater that you have been revamping, there could be corrosion issues if you don't have the right material grade selected in your HVO unit. So if you have a lower material grade available, you might need to invest in more pretreatment to remove the fatty acids. Used cooking oil is another feedstock, which is very interesting. It has a very high chloride content, so yes, more pretreatment again is going to be needed. So more flexibility in your feed pretreatment step. Finally, if we talk about tallow or animal waste, another feedstock which is very interesting, but it also has a high content of polyethylene, which needs to be removed before you can feed it to your HVO unit. So again, more pretreatment is needed. And in Europe, Some parts of the animal waste, some categories are also classified as biohazardous waste because of mad cow disease. And you need to be aware of it so that your feed pre-treatment and your handling of both feedstock and waste is according to requirements. So if we are looking at the different feed pre-treatment steps required, as we said, with crude palm oil with very low phosphate content, you actually only need one pre-treatment step, and that's an adsorption, where clay is being used to precipitate and take care of the phosphate compounds. You will get a byproduct, which is spent clay, which contains residual oils, soaps, and metals. But after that, you have a pre-treated feedstock ready to go to your HVO. For all other seed oils where you have a higher phosphate content, you also need to have a degumming section. Degumming can be of various kinds. It can be just hydration, washing with water, or it can be chemical, which means you are treating it with a weak acid, or it can be enzymatic degumming, where you need an enzyme to remove the phosphate compounds from the feedstock. The byproduct from degumming is wastewater containing all these phosphorus compounds that you have removed. And that wastewater needs, of course, to be treated. If we jump down to the lower section, you have your used cooking oil. The used cooking oil contains a lot of chlorides, which needs to be removed before you send it to the degumming section. That's again a water washing, which then creates a wastewater containing chlorides. Then you can continue with the degumming. With tallow, you need to do both chloride mitigation plus polyethylene removal. Polyethylene removal is again another adsorption step where you get byproduct spent clay with residual oil, metals, and polyethylene. And after that, you can send the tallow for the degumming. If you have these 4 different process units in your feed pre-treatment plant, you will be having a very high flexibility to handle most feedstocks available in the market. All of these processes are operating at quite low pressures and temperatures if you compare to normal refinery processes. So in that sense, you could say that they are more safe, there are less risk of operating them. But there are, of course, other safe and healthy issues that you need to be aware of. And one of the most important thing is the self-ignition of a lot of the feedstock that is being used for the HVO pre-treatment. So you need to be very careful with oil spills to make sure that you don't get a dangerous situation in your pre-treatment unit. And as I mentioned before, if tallow is being used as feedstock, you need to be careful if it's classified as biohazardous waste. That was all about the feed pre-treatment. Next, I'm going to talk about your HVO processes, and I'm going to talk about the fractionation section, the stripper and fractionation section. The hydrotreater and the reactor section itself is a little bit different compared to a normal refinery hydrotreater. It's a very exothermic reaction because of a lot of free oxygen available in the feedstock. So a lot of energy is going to be produced in the reactor section. And so you are going to need to have a lot of different means to remove this energy from the process. So if we start looking at this fractionation section, one interesting opportunity that you have is, of course, to optimize the pressure at which you run the fractionator. If you can reduce the pressure in the fractionator, it means less energy input required in the reboiler or in the fired heater of the fractionator. But it also means a better split between close boiling range products, such as the bio-naphtha and the biojet. So it means you can increase the production of biojet over naphtha. So how are you going to reduce the pressure in the fractionator? Well, one obvious way is, of course, if you can minimize the pressure drop in the overhead condenser. So by using heat exchangers that can operate with lower pressure drop, it means you can reduce the pressure in your fractionation section. Another way is if you can also use heat exchangers that can cool and condense the overhead vapor to a lower temperature, a temperature closer to the supply temperature of the cooling media. So by using welded type plate heat exchangers, where you can have only a 5-degree approach temperature to the cooling media, it actually means that you can reduce the pressure in the top of the column at which you are condensing your overhead vapor, which means you can also then reduce the pressure in the flash zone of the column. Cooling and condensing your overhead vapor to a lower temperature also means that you will minimize the amount of off-gas that is produced that you need to send to the sulfur recovery section for treatment. And you will maximize the liquid production of naphtha from your plant. So optimizing the pressure in the column and the pressure in the overhead section of the fractionator is very interesting to maximize the efficiency of your fractionator. Other things you can look into is, of course, to maximize the heat recovery in your bottom feed interchanger. So you maximize the inlet temperature of the feed to the fractionator, and again, you are offloading the reboiler. And you can also look into waste heat recovery. And you will see that in a later section, how a refinery are optimizing and maximizing waste heat recovery from the hot rundown streams to use this energy for interesting purposes in other parts of the plant. But if we start looking into a feed effluent interchanger, this is an isomerization stripper, which is optimized with maximum heat recovery in the feed bottom interchanger, which is a welded type plate heat exchanger. Here, the energy recovery is increased with 42%, meaning that the energy consumption in the reboiler is reduced with $600,000 per year. On top of that, the downstream product air cooler doesn't need to be operated any longer because of insufficient cooling of bottom product is achieved in this interchanger. This interchanger has been operating since 2010, so it's more than 10 years in operation. And here to the left, you can see 2 years of operation, and you can see that it is very stable performance over this period. So finally, we will talk about your wastewater management. As I already mentioned, there are 2 processes in the feed pretreatment plant that are going to produce quite much wastewater, and wastewater maybe with a different kind of character compared to normal refinery wastewater. In the degumming section, there will be around 5 to 10% of water to the oil flow, and that will then be a wastewater with a phosphorus content. For the chloride mitigation section, you also have around 5 to 10% to the oil flow, but normally there is less oil flow that needs to be treated in the chloride mitigation section. So it's normally less wastewater, and sometimes some of that wastewater could actually be used from the degumming section. But there is still going to be a high amount of wastewater produced, and of course as well from the hydrotreater section, the deoxidation reactor, there is a lot of wastewater being produced. You need to see if your existing wastewater treatment plant can handle this amount and these kind of impurities, or maybe you need to do investments in your existing wastewater treatment plant to debottleneck it and make it fit to handle more capacity. Or you can do what a refinery in Europe is planning to do. This is a new HVO complex of a capacity of 2,800 cubic meter per day, producing green diesel and jet fuel. They are going to install in a zero liquid discharge evaporation system. So they have around 34 tons per hour of wastewater, which contains 0.7 to up to 3% of fatty matter. That's being sent to an evaporation plant where it is concentrated, and the waste coming out is less than 1 ton per hour, with 30% fatty matter, so more or less a zero liquid discharge system. In addition to the advantage of sending a much lower content of waste to your wastewater treatment plant, this plant will also produce condensate, which can be recycled back to your pre-treatment plant to be used in your degumming and your chloride mitigation section. This plant will produce almost 42 tons per hour of condensate. To run this plant, the refinery needs fresh steam. They need around 8 tons per hour of 4 bar atmospheric fresh steam to run this evaporation plant. However, what this refinery is planning to do is a waste heat recovery in the fractionation section. So by cooling down the hot products before going to tank, they will generate 10 tons per hour of 4.2 bar gauge steam from the hot rundown steams. So that steam can be used to run this zero liquid discharge plant to minimize the waste going to the wastewater treatment plant. On top of the steam generated, this refinery is also recovering another 15 megawatt into a hot water loop, which is around 400 tons per hour at 95 degrees C, that will be used for boiler feed water preheating or district heating in wintertime. So by combining energy recovery from the HVO plant, you can evaporate and concentrate your waste coming from the HVO complex, and you can produce water that will go back to your pre-treatment plant in your HVO complex. So these three parts in your plant are very closely interconnected, and by optimizing how each one of them is performing and how they are operating together, you can maximize your feedstock flexibility and get your longest catalyst life cycle. You maximize your product yield and your energy efficiency. You minimize capex that goes into this new HVO complex, and you minimize your waste and your environmental footprint. So I hope you find this presentation interesting and that it gave you some idea on what you can be doing with your HVO complex. And if you have more questions, please feel free during the Q&A session, or by coming to our e-booth, or by sending a meeting request, and we can discuss your HVO complex in detail. Thank you very much and have a great day.